One, two, three. Though the ocean may sometimes appear to be still, it is always moving, even at great depths. In fact, the ocean moves around the entire world in a circulation pattern called the ocean conveyor belt. In contrast to wind-driven surface currents, deep ocean circulation is driven by changes in density. Recall that less dense water remains at the surface, while denser water sinks. Waters of different densities tend to organize into layers, with the densest, coldest water on the bottom and warmer, less dense water on the top. It is a movement of these density layers that create the deep sea water circulation. Since water density depends mainly on temperature and salinity, this circulation is referred to as thermohaline circulation. There are only a few places on Earth where the environmental conditions change the density of the seawater in a way that results in the formation of deep water. Deep water formation simply refers to the process that seawater sinks from the surface to the deep ocean. The main processes that increase seawater density are cooling, evaporation, and ice formation. Evaporation and ice formation cause an increase in density by removing fresh water, leaving the remaining seawater with greater salinity. The main processes that decrease seawater density are heating and dilution by fresh water through precipitation, ice melting, or freshwater runoff. Note that all of these processes exert their effects at the surface, but don't necessarily affect deeper water. However, changing the density of the surface water causes it to sink or rise, and these vertical, density-driven movements create the deep ocean currents. These thermohaline currents are slow, on the order of 10 to 20 kilometers per year, compared with the surface currents that move at several kilometers per hour. Temperature and density are inversely proportional. As one increases, the other decreases, and vice versa. Salinity and density are directly proportional. As one increases, so does the other. As temperature depth increases, so does salinity, but temperature decreases because cold water sinks. A temperature salinity (TS) diagram is used to examine how temperature, salinity, and density change with depth, and to identify the vertical structure of the water column, including the water masses it contains. Water temperature is on the y-axis, and salinity appears on the x-axis. A TS diagram shows line of equal density, or isopycnals, for various combinations of temperature and salinity. You can plot the values of temperature and salinity on the diagram and use your point of intersection to calculate the density of the water. Here in the example, a temperature of about 11 degrees Celsius and a salinity of 34.6 PSU results in a density of 1.0265 grams per centimeter cubed. Surface water cools as it flows towards the polar regions. Salt doesn't freeze, therefore, when seawater is exposed to freezing temperatures, only the fresh water freezes. The ice crystals expel salt into the surrounding water, which increases the salinity of the water. As the water gets saltier and colder, it gets denser, which causes water to sink. This sinking, cold, salty water marks the beginning of the global circulation pattern called the ocean conveyor belt. The adjective thermohaline derives from thermo, referring to the temperature, and haline, referring to the salt content, factors which together determine the density of water. Wind-driven surface currents, such as the Gulf Stream, travel polewards from the equatorial Atlantic Ocean, cooling en route, and eventually sinking at high latitudes, forming the North Atlantic Deep Water, NADW. This dense water then flows into the ocean basins, while the bulk of it upwells in the Southern Ocean. The oldest waters, with a transit about 1,000 years, upwells in the North Pacific. Extensive mixing therefore takes place between the ocean basins, reducing differences between them and making the Earth's ocean a global system. On their journey, the water masses transport both energy in the form of heat and materials, solids, dissolved substances, and gases around the globe. As such, the state of circulation has a large impact on the climate of Earth. Deep ocean currents, referred to as thermohaline currents, are caused by density differences. Colder saline water masses are more dense and they sink, while warmer freshwater masses are less dense. Warmer water masses are found near the equatorial regions, and colder water masses are found near the polar regions. Less saline water is found where there is more precipitation or river input. More saline water masses are found in areas where there's a lot of evaporation because salt is left behind in the water, or in polar areas because as ice forms, salt is left in the water. Accordingly, the most dense ocean water, water with the lowest temperature and highest salinity, is found in the North Atlantic Ocean. This cold saline water sinks because of its greater density, and then it flows southward deep along the ocean floor of the Atlantic Ocean through the Indian Ocean, eventually mixing with the currents in the Pacific Ocean. The surface current flows back through the Indian Ocean into the Atlantic Ocean, returning surface water to the North Atlantic Ocean and driving the Gulf Stream. The Gulf Stream flows along the east coast of the United States and across the northern region of the Atlantic coast, causing Great Britain and Europe to have fairly moderate temperatures. The rising and cycling and sinking water transports between the surface and the deep circulation is referred to as the global oceanic conveyor belt. This is a very slow process. It takes upwards of 1,000 years to complete the cycle. The formation of dense deep water at high latitudes drives the slow, steady movement of the warm surface waters towards the poles. It is referred to as the ocean conveyor belt and is responsible for moving significant amounts of heat from the equator towards the poles. So why is thermohaline circulation so important? The ocean conveyor belt regulates climate by transferring heat, affects the cycling of nutrients, transports oxygenate, pause. One, two, three. Why is thermohaline circulation important? Well, the ocean conveyor belt regulates climate by transferring heat, which affects the cycling of nutrients, and transports oxygenated water into the deep ocean. There are less nutrients in the surface ocean because they are used by photosynthetic marine plants called phytoplankton. During photosynthesis, phytoplankton produce and release oxygen into the surface of the ocean. Additionally, oxygen is mixed into the ocean from the atmosphere at the surface and is consumed by organisms breathing. Because oxygen is both produced and consumed, oxygen levels in the surface ocean vary geographically. In the deep ocean, there is no photosynthesis or contact with the atmosphere. The only way oxygen gets into the ocean is when the surface water at the poles cools and sinks, bringing oxygen into the deep ocean. In the deep ocean, oxygen is only consumed, not produced. Therefore, oxygen levels can only decrease as the water moves through the deep ocean. Scientists agree that global change is occurring. How will climatic differences in all ocean pause? 1, 2, 3. Scientists agree. Pause. 1, 2, 3. Scientists agree that global change is occurring. How will climatic differences affect the ocean conveyor belt? Sea ice and glaciers are already melting, and precipitation is predicted to increase in the Arctic. The combination of increasing precipitation and melting ice will decrease the salinity in the ocean where deep water is formed. Such changes in ocean density could stop the formation of the cold, salty, deep water that powers the ocean conveyor belt. A change in the ocean conveyor belt would affect the climate by changing the way heat is transferred on Earth. End